Hello there, and welcome to the Shots in the Quark Special Relativity course. In this course, we're going to introduce the mathematical and conceptual foundations of Einstein's theory of special relativity. As part of this course, you'll find notes, exercises, and solutions to help you get to grips with all of the basic special relativity material that you'll need to be able to solve problems and to understand physically what the theory actually tells us. But before we start delving into the specifics of special relativity, I'll just say a few words on the experience one might expect to have while studying the subject for the first time. Although relativity may seem like quite a daunting subject to tackle, what with all the length contraction and clocks ticking at different rates depending on how fast you're moving, the actual mathematics of the subject is fairly straightforward. All you need to start studying special relativity is a knowledge of ordinary Newtonian classical mechanics, some familiarity with vectors and how to write Newtonian mechanics in vector forms, and finally just some familiarity with matrices at the level of, say, an A-level further maths course. That's really all the mathematics you need. So what makes relativity a difficult subject to study? Well, the most challenging part about the subject is to understand the physical interpretation of all the equations and mathematics that you're writing down on the page. It's fairly straightforward to solve relativity problems mathematically. What's difficult is to understand physically what's going on and how the mathematics relates to the physical situation. So with that in mind, one of the main aims of this course for me is going to be to try and convey as clearly as possible the physical intuition behind relativity. I want you to really understand physically what is going on in any relativistic system. I don't just want you to be able to manipulate the mathematics, solve equations, and write down a number at the end of a calculation. I think that's more than enough preamble for now, so without further ado, let's start doing some physics. Right, here we go. Special relativity. In this video, we're going to be starting with Chapter 0, which I've called the preliminaries. This is about some concepts in physics and some mathematical tools that are really at the foundation of all of special relativity. Now, most of these concepts actually already apply even in ordinary classical mechanics. You just may not have noticed them or have had to think about them in any particular detail. But in special relativity, these concepts take center stage. So we need to make sure that we have a clear understanding of these concepts in the context of classical mechanics so that then we can apply them with some good intuition already to build up our theory of relativity. In this chapter, we'll take a look at three things. One physical concept, that of a frame of reference. One mathematical concept, that of a coordinate transformation. And finally, we'll look at the basic mathematics of matrices. To get started then, we need to talk about frames of reference. What is a frame of reference? Well, a frame of reference is something that actually applies even in Newtonian physics. Whatever you're doing in classical mechanics, you need to define what frame of reference you're working in. But you may not have noticed having to work with these things before because in classical physics, most physically relevant quantities that you're working with are the same regardless of which reference frame you're using. For example, in Newtonian physics, every observer in any reference frame is going to agree on the order in which a series of events occurred. But this is not the case in special relativity. In relativity, different observers, depending on how they're moving, are going to disagree over the ordering of a certain series of events. So although you never noticed using frames of reference in classical mechanics, even though they were always there, now in special relativity they become much more important, and we need to be very clear on what they are. So, what is a frame of reference? A reference frame is defined by some physical object which we call the reference body. The reference frame is then basically just what the universe looks like from the point of view of that reference body. Some common frames of reference include yourself. Obviously, there's something that the universe looks like from your point of view. If you ever travel in a vehicle, such as a plane or a car, then that vehicle can act as a reference body and define a frame of reference. If you're in a room or a laboratory and conducting some kind of experiment, then your frame of reference will be the laboratory that you're in, and is often called the lab frame. Or if you're working on solar system scales, you may take the fixed background of stars to act as a reference body to define a reference frame to study the solar system in. So you can take any object, even a composite one like the fixed background of stars, and it defines a reference frame from which you're going to do your physics. It's the point of view that you're about to talk about physics from. Once you've set up a reference frame, you can start talking about motion. Something is moving if it is moving with respect to the point of view of the reference body that defines your frame of reference. But obviously, we want to say more than just whether an object is moving or not. We want to measure motion much more precisely. Once we have a reference frame, we can use it to set up a coordinate system. It's important to distinguish between a frame of reference and a coordinate system. A frame of reference is a physical concept. Each object has its own frame of reference. A coordinate system, on the other hand, is a mathematical way of labeling the points in a reference frame. Each object defines its own unique reference frame, but within that reference frame, we can set up any coordinate system that we like. So in a single reference frame, there are an infinite number of different coordinate systems which you could set up to label the points in that reference frame. But how many reference frames are there in the universe? Well, in contrast to a coordinate system, which is really just a mathematical tool for labeling points, a reference frame is something physical. A reference frame is defined by the point of view of an actually existing physical body, its reference body. So there are as many reference frames in the universe as there are physical objects. Every electron, every individual electron, has its own reference frame. Every human has their own reference frame. Every planet, every star, every physical object defines its own reference frame. What special relativity is really about is how to compare descriptions in different reference frames. Now, if every object has its own reference frame, then every object basically has its own description of how the universe is behaving. So every physical object has its own reference frame, which basically means every physical object has its own description of what's going on in the universe. At this point, you might start to wonder if physics is entirely subjective. If every object has its own reference frame and describes the universe within that reference frame, then it feels like every object is kind of living in its own universe. Is there anything objective we can say about the universe as a whole then? Yes, we can. Every reference frame will have its own description for what's going on in the universe, but this description must be internally consistent. What special relativity tells us then is how each of these individual, internally self-consistent descriptions of the universe relate to one another. It also tells us what each of these individual descriptions actually all agree on. And those things that they all agree on, which we call invariants, are the objective physical facts. So to go through all of that again, each object has its own reference frame, and each reference frame is its own totally valid, totally self-consistent point of view of the physics in the universe. The thing that may seem a little strange, however, is that different reference frames don't necessarily agree on everything that they each measure. In Newtonian mechanics, different reference frames basically agree on nearly everything. There's a universal time in all reference frames, so every reference frame will agree on both the time at which an event occurred and also the order in which events occur. And every reference frame will also agree on the size and shape of any particular object. The reason why special relativity may seem so strange compared to Newtonian physics is because these things that we used to think were the same from every point of view actually aren't. In special relativity, reference frames moving at different speeds with respect to one another will not agree on the time at which an event occurred, the order in which events occur, or the size and shape of an object that they both observe. But despite all of these disagreements, there are things that every observer will agree on in special relativity. In one sense, you can think of special relativity as being a bit like a murder mystery. In a murder mystery, each suspect has their own story or alibi. Each suspect's alibi must be internally consistent. If there are contradictions in their story, it's obvious that they're lying. But there may be some elements of each suspect's alibi that disagree with some of the other stories that the suspects are telling. Special relativity then is a bit like the detective. It pieces together the whole picture, the true story, from each individual description, and it also tells us how each of those individual descriptions relates to one another. And that's what we're going to move on to next. How can we relate what is observed in different reference frames? To answer this question, we're going to need to understand coordinate transformations. But we'll leave that for next time. In the meantime, thank you very much for watching, and I hope you found this section on reference frames interesting. Please do leave a like and subscribe, and I hope to see you on the next video where we'll be discussing coordinate transformations.